Hi, in this quick start video, I am presenting Settle BI, an integrated platform for semantic business intelligence that bridges semantic web and business intelligence technologies. Here you will be looking how to use Settle to build a semantic data warehouse and apply OLAP queries on it. In this demonstration, we use the population dataset for Bangladesh Census Data 2011 as use case. The population cube is composed of three dimensions: living position dimension, residence dimension, and geography dimension. And we have only one measure, and it is number of people. The levels of each dimension are organized in different hierarchies. The first step is to design the T-box of the semantic data warehouse. Next, creating a box from the semantic data warehouse and then apply OLAP queries on it. As you see here, Settle is organized into three layers: definition layer, ETL layer, and OLAP layer. User can create a new target T-box or edit existing target T-box by clicking here. Let's see how to create a new one. Click New T-box button. Type a name. Choose the desired format and directory to be saved. So the very common prefixes are written by default. You can create a new IRI or edit the existing one. Prefix name and IRI. Okay. The leftmost panel allows you to create different OWL and data warehouse constructs. Let's create a dimension. Select prefix, type name, level. Okay. Now create a measure. Select prefix, type name and level. Okay. Then create a cube. Select prefix of the cube. Type a cube name. Add measure from the measure list. You can select aggregate function. Then add an measure component. And select dimension from the dimension list. Select the cardinality and add the dimension component. Click OK. In this way, we can create different constructs. The corresponding triples for the constructs are generated internally and shown in the middle panel. Now you can save it. Now let's open the target T-box we explained in our use case. Here we can see different multidimensional constructs: dimensions, hierarchies, level properties, level attributes, cube, and cuboid. A cube is defined in terms of fact and dimensions, where a cuboid is defined in terms of facts and levels. We can also add new construct or edit it. The rightmost panel shows the description of the selected construct, and it also allows editing and adding and editing the components of the construct. For example, if we want to change this range, we can do it by clicking the update button and selecting the desired value. So once a target is defined, the next task is to map between the sources and the target. You can select source and target files to be mapped. First task is to create a mapping dataset. Therefore, each source and target pair will be a dataset. Under a dataset, you can create concept mappings. Let's map between the target cuboid dataset and source facts concept. Select the relationship between them. Now the instance level mapping. You can select whether all instances of the source concept should be mapped or a subset of the instances. How to create the values of the array of the target instances. It can be a source attribute or a source or as same as source instance or incremental or an expression. Here we want to make an expression by concatenating all the properties of source concept. The next task is to map in property level. Here we can choose under which concept mapper the property mapper will be created. Select the target property. The values of the target property can either be same values of the source property or it can be an expression. Now we can save it. The corresponding triples for the mappings can be shown in the mapping file editor. The mappings can also be used for intermediate mapping. Intermediate mapping is used for the transformation on RDF literals. Let's open the mapping file of our use case. Here is the mapping file of our use case. So the mappings are defined in our own vocabulary. You can see the different components of the file in the leftmost panel. The rightmost panel allows you to edit the mapping components. So the next task is to create the ETL flow to populate the target evokes. We can create a new ETL from the file menu. The left-hand side is showing all operators. It includes operations for extracting data from semantic and non-semantic source. RDF wrapper. It converts non-semantic to RDF. Tbox deriver. Derive Tbox from non-semantic source. Tbox from RDF evokes. Sometimes the RDF file only contains the assertion. So this operation derives the Tbox from that assertions. Instance generator. Label entry generator. That means it creates label members. Fact entry generator. Update dimension construct. It addresses the slowly changing dimension issue. Your load operator is used to load data into a tuple store. Here we use generate. So you can drag and drop the operators. Control flow is used to connect the operators. In the paper, we showed how the operations are connected using an ontology. Let me show you one example how it works with fact entry generator. The input can either be a CSV or RDF. The path of the source file. Select a mapper location. That means the mapping file we did from source to target. Provenance graph location. Actually, provenance graph stores the IRI generation information. Target box location and select the target box location. Yes. So if all the input are given correctly, the color of the operation will be changed. Now we can run it. It will take some time. The status
of the ETL
in the status bar. So let's open the ETL of our use case. Here is it. So now we have our target box. We have now our target box. Now let's open our OLAP layer to trigger or to issue some OLAP query. So this is our OLAP interface. User can create and run OLAP queries on their target. The target can be accessed either from a local file or through an endpoint. Let's load our target from local files. It will take them some time to load. So as soon as the files are loaded, we can extract the cube structure from it. Cube structure contains dimension, corresponding hierarchies, and the levels of the hierarchies, and you can see here measure with aggregate function. Then user can create OLAP query to explore and aggregate measures at various levels of details. Let's make a query. Here we have 3 dimensions: living position dimension, geographic dimension, and residence dimension. The corresponding hierarchies are shown under a subnode of dimension node.
Let's create the query. We want to aggregate the measure in administrative unit 1 level, 2 level, not 1, so remove it, administrative level 2, and living position residence type from residence hierarchy, and position all from living position dimension. So let's run. Okay, get a result. No, you must select the data set. Okay, so we want to see sum and average. See here we can see the result at administrative unit 2 for in geographic dimension, and residence type either rural or urban, and living position all. That is, yeah. So we can see sum and average. Yeah. Let's apply some slice and dice query. So we don't want to see in administrative 2 level. We want to see it at administrative level 1. And here you can select by the filter by on property value. For example, here we can by this one, or administrative name, we want to select body shell and corner division. Result. Here we see that list rural and urban.